Breadth-First Search, abbreviated BFS, is a systematic way to explore every vertex node of a graph level by level. Imagine you are standing in a city square and you want to visit every building that is exactly 1 block away before you go 2 blocks away, then 3, and so on. BFS starts from a chosen source vertex and first visits all its direct neighbors, distance 1, then the neighbors of those neighbors, distance 2, etc. The traversal never jumps ahead to a farther vertex until all closer vertices have been processed. This layer-by-layer approach guarantees that the order of discovery corresponds to increasing graph distance from the source. Mathematically, let d of s, v be the length in edges of the shortest path from source S to vertex V. BFS discovers vertices in non-decreasing order of d of s, v. For an undirected, unweighted graph, BFS therefore produces a shortest path tree rooted at S. The algorithm can be applied to both directed and undirected graphs. When applied to directed graphs, it follows only outgoing edges, which effectively computes reachability distances in the directed sense. Practical example: in a social network, performing BFS from a person yields the friends of friends hierarchy, where level 1 are direct friends, level 2 are friends of friends, etc. In a maze, BFS expands all cells at distance k from the entrance before moving to distance k+1, guaranteeing the shortest escape path is found. Breadth-first search of G with source S. For each vertex V in G, color of V equals white, not visited. Distance of V equals infinity. Predecessor of V equals n. Color of S equals gray, discovered. Distance of S equals 0. Predecessor of S equals n. In QS onto QQ. While Q is not empty, U equals dq of Q. For each vertex V in adjacency of U. If color of V equals white, color of V equals gray. Distance of V equals distance of U plus 1. Predecessor of V equals U. In QV onto QQ. Color of U equals black, finished. Color scheme: white means undiscovered, gray means discovered but not fully explored, black means finished. This prevents revisiting vertices and ensures each edge is examined once. Distance stores the number of edges from the source. It is built incrementally as distance of V equals distance of U plus 1. Predecessor records the predecessor of each vertex, which can later be used to reconstruct the breadth-first search tree or a shortest path. Q implementation. In Python, collections.dec provides O1 amortized in Q and dq. In C++, the standard Q wrapper around standard dec is typical. Adjacency representation. An adjacency list of vector of integer or dictionary of integer to list of integer, is preferred for sparse graphs because it uses O of V plus E space and allows O1 neighbor iteration. A concrete Python snippet. From collections, import dec. Define BFS with parameters graph and S. Color equals a dictionary mapping each vertex V to white for V in graph. Distance equals a dictionary mapping each vertex V to float of infinity for V in graph. Predecessor equals a dictionary mapping each vertex V to none for V in graph. Q equals dec containing S. Color of S equals gray. Distance of S equals 0. While Q is not empty, U equals pop left from Q. For each vertex V in graph of U. If color of V equals white, color of V equals gray. Distance of V equals distance of U plus 1. Predecessor of V equals U. Append V to Q. Color of U equals black. Return distance and predecessor. Time complexity. Every vertex is enqueued and dequeued exactly once, which is O of V operations. Each edge U, V is examined exactly once when U is processed, which is O of E operations. Hence, total time is O of V plus E, linear in the size of the graph. For dense graphs where E is approximately V squared, the time grows as O of V squared, but the algorithm is still optimal for an adjacency list representation. Space complexity. The Q can hold at most all vertices of one breadth-first search frontier. In the worst case, for example, a complete binary tree, the frontier size is O of V. Additionally, we store 3 arrays or maps of size v, color distance predecessor, which is O of v extra space. The adjacency list itself needs O of v plus e space, which dominates when the graph is dense. Thus, breadth-first search runs in linear time and space relative to the input size, making it suitable for very large sparse networks. While BFS runs, it implicitly builds a BFS tree rooted at the source vertex. The pred array records for each vertex its parent in the tree, that is, the vertex from which it was first discovered. All vertices at the same distance from the source appear at the same depth in this tree. This is called the level order property. Formally, for every vertex v reachable from S, the unique path obtained by repeatedly following pred of v back to S has length dist of v and consists solely of edges traversed by BFS. Consequently, the BFS tree is a shortest path tree. The path from the root to any node in the tree is a shortest path in the original graph. Practical example: in a social network graph, the BFS tree from a person shows all friends, level 1, friends of friends, level 2, and so on. The tree can be extracted after the algorithm finishes by iterating over all vertices and linking each vertex to its predecessor. Visualization tools often draw this tree with concentric circles or horizontal layers to emphasize the level order. Correctness of breadth-first search can be proved by induction on the level number k, distance from the source. Base case k equals 0. The source S is enqueued first, colored gray, and its distance is set to 0, true by initialization. Inductive hypothesis. Assume that after processing all vertices at levels less than or equal to k, every vertex v with shortest path distance d of S to v equals k has been discovered, colored gray, and distance of v equals k. Inductive step. When a vertex u at level k is dequeued, breadth-first search examines each neighbor w if w is white. Then the edge from u to w provides a path of length k plus 1 from S to w. No shorter path exists because any path shorter than k plus 1 would have to reach w at a level less than or equal to k, contradicting the hypothesis that w is still white. Hence, breadth-first search discovers w, sets distance of w to k plus 1, and enqueues it. Consequently, after all level k vertices are processed, all vertices at distance k plus 1 are discovered. By induction, breadth-first search discovers vertices in non-decreasing order of their shortest path distance, proving that the distance values are correct and that the predecessor links form a shortest path tree. In an unweighted graph, the length of a path is simply the number of edges. Because BFS discovers vertices in order of increasing distance, the first time we reach a target vertex T, we have found the shortest path from the source S to T. The path can be reconstructed by following the pred links from T back to S. Dist T equals D. Then there exists a path of length D and no path of length D minus 1 or less, which is the definition of shortest path in an unweighted graph. This property is used in routing, minimum hops, maze solving, fewest steps, and social network analysis, minimum degrees of separation. Example: in a grid graph representing a city block layout, BFS from a corner finds the minimal number of blocks to any other intersection. The algorithm simultaneously computes the distance to all reachable vertices, making it useful for multi-destination planning. Both breadth-first search and depth-first search explore graphs, but they do so in different orders. BFS advantages: finds shortest path distances in unweighted graphs. Produces a level order traversal useful for layering problems, for example bipartite check. Guarantees that the first time a vertex is seen, it is via the shortest path. DFS advantages: uses less memory on sparse graphs. Recursion stack depth is at most v. Naturally discovers connected components, topological order, articulation points, and bridges. Limitations of BFS: requires an explicit queue which may hold many vertices, worst case O of v. Not suitable for deep search, where you need to go far along a single branch, for example puzzles with many moves. Use cases: BFS short route in road maps, spreading of information or disease level by level game AI bipartite testing. DFS detecting cycles, ordering tasks, topological sort, solving constraint satisfaction, puzzle Sudoku n queens where backtracking is essential. In practice, the choice depends on the problem's nature. If distances matter, BFS is preferred. If structural properties or exhaustive search are needed, DFS is often more appropriate. Typical exam questions often ask students to write BFS pseudocode, analyze its complexity, or apply it to a concrete problem. Common edge case scenarios include bipartite check. While performing BFS, color each vertex with one of two colors, say 0, and one adjacent vertices must receive opposite colors. If a conflict occurs, the graph is not bipartite. This test runs in big O of V plus E. Connectivity after BFS from an arbitrary source. If any vertex remains white, the graph is disconnected. The number of BFS runs needed to visit all components equals the number of connected components. Graph with isolated vertices. BFS starting from an isolated vertex visits only that vertex. The algorithm must still handle empty adjacency lists gracefully. Directed versus undirected. In directed graphs, BFS follows only outgoing edges. Students may need to explain the difference for reachability. Multiple sources. BFS can be started simultaneously from a set of sources. For example, multi-source flood. Fill all sources are in queued, initially producing distances to the nearest source. Exam questions may present a small adjacency matrix or list and ask for the order of vertex discovery, the BFS tree, or the distance array. Understanding the queue mechanics and color handling is key to answering correctly.